right?
So once you get kind of like the details ironed out, this is a pretty quick way to develop and work with Verilog. Now we can simulate these designs. We could use the Icarus system, and we could use GTK wave, right? But if you're going to do that, you need to generate the clock yourself. So you use an initial and a always statement in the initial block and just toggle a clock every few nanoseconds. But you don't make it count up to 50 million if you're going to simulate it, because you'll have to get 50 million ticks before, right? So you set it to toggle every like 5 or 10 clock ticks instead. So you can simulate it in the Icarus system. You can also simulate it in the Xilinx tools. And there's a section in the Mimas board documentation that tells you how to set up a test bench in the Xilinx tool chain, right? And you basically say a new module, you say you want a test bench, you tell it which module you're testing, and it sets up a framework for you, and you just drop in your input stimulators and go ahead and run it. Yeah?
Is there a limit to how fast you can make an LED flash?
Nope.
Just a diminishing
But you won't
return?
notice it beyond a certain point.
Gotcha.
So we could simply connect this to the clock, and every time the clock changed, we could toggle the state of the LED, and that would toggle 50 million times a second.
Just a dimmer or not even looking?
At 50 million, you're not going to notice it. At a frequency that's too fast to notice, sometimes you can still detect it by, say, spinning a spoked bicycle wheel in front of it or shaking salt in front of it, and you'll get a stroboscopic effect, right? At higher frequencies, you can hook it up to a speaker and you can get a tone. That'll get you up to several thousand oscillations per second. Beyond that, you gotta go to like an oscilloscope or something official.
Okay.
But if you're on a desert island with a salt shaker and a speaker, right, you can still debug these circuits. So that works. In 270, we'll talk about ways you can do things like control the brightness of an LED, though, by making it blink. Because in some cases, what we can do is we can turn it on for, you know, a millisecond, and then turn it off for a millisecond. Turn it on, turn it off. And you may not see it blinking, but what your eye will detect, your eye and brain will detect, is that it's half as bright as usual, because it's basically putting off half the energy. And if you turn it on for a millisecond and then turn it off for 2, and on for 1 and off for 2, it'll be about a third as bright. And we can actually control the intensity of an LED, even though the actual LED is either on all the way or off all the way. We can make it look to a viewer like there's different levels of intensity by doing this modulation. It's what we call pulse width modulation. We'll do a lot of that in 270.
Is that how dimming works?
That's one way. That's one way that regular lights can be dimmed. It's also how a lot of motor control is done. When you want to control a motor with a microcontroller, usually you're either turning the motor on or off, right? And if it's on, it's spinning at full speed. If it's off, it's coasting. But by modulating the output, you can make it spin at variable speeds, and that's commonly done. So this is all stuff we'll do in summer if you're in 270. And that's fun stuff. All right, did we play with glitches at all in Verilog? So here's, so we're back in Icarus system, right? Here's some Verilog code, and it's a module named glitch, and you know that can't end well, right? So what are we building here? We're building a box with one input A and one output x. And I have two assigned statements. I'm saying A bar is the inverse of A. So I've got A going into an inverter, and I'm calling that output A bar. And then I'm setting x equal to the logical AND of A with A bar. So here's what the circuit looks like that we're defining in Verilog. A goes in, x comes out. X is equal to A ANDed with A bar. All right, well, what do we expect x to be equal to for different values of A?
It's just 0 all the time.
It's always 0, right? We can be explicit. A has got to be either a 0 or a 1. A bar is going to be the opposite. And then if we take A and A bar and we AND them, we're always going to get 0. I don't know why Clark Student keeps wanting its blue sky password. But there you go. So x is A ANDed with A bar, should always be a 0. Well, what we've done here in the Verilog is we added these number sign 5 and number sign 2 in the middle of the assign statement. And these are delays that we're asking this thing to introduce into the simulator. So what we're saying is that A bar is equal to the inverse of A, but it takes 5 nanoseconds for that output to change. So we're putting in a propagation delay of 5 nanoseconds in that inverter. And in the second assign statement where we do the AND, we're putting in a 2 nanosecond propagation delay. So now we've got something like this. 2 nanoseconds here, 5 nanoseconds here. And remember when we talked about timing diagrams, we talked about glitches, we saw that if we build this kind of circuit, sometimes we get a glitch. Sometimes the output's not 0. Because what can happen is if you input a 0 to A, you've got a 1 coming in here and a 0 here. If you suddenly change A to a 1, this output will still be a 1 for 5 nanoseconds. And for a brief period of time, we're going to have a 1 on this line, and we're going to have a 1 on this line. And the AND gate will pick that up, and 2 nanoseconds later, its output will be a 1. So glitches can be tricky to detect. But Verilog can help us with that. So here's our whole module, right? Register A, wires A bar and X, and we have these 2 assignment statements. And then I have a test file. So the test file will set A to 0, wait 20 nanoseconds, set A to 1, wait 20 nanoseconds, set A back to 0. So we'll compile that. We'll run it. It creates a VCD file. We'll go into GTK wave. And let's drop some waveforms in here. So this is A. Now let's just look at A and X. And let's zoom out. And there's a glitch. Right? We expect X to always be equal to 0, and it mostly is. Right? 0, 0, 0, 0. But right here, X becomes a 1. And it stays a 1 from 22 nanoseconds all the way out to 27 nanoseconds. So it's a 5 nanosecond glitch. And then it goes back to a 0. But every time that A changes from a 0 to 1, we're going to get this little glitchy output in X. And we can look at A bar and see why that's happening. Right? And it's because A bar is taking a while to respond to this change in A. So for a brief period of time, A and A bar are both 1. Now it doesn't happen when A drops, because the glitch here is that A and A bar are both 0, and that doesn't change the output of the AND. So we can use Verilog to help us with our timing analysis, help us find glitches in the behavior of our circuit. So, any questions? So let's do something fun.